We are going to look at several superheroes today and determine how or how they don't break the laws of physics. We'll start with Superman first. There's definitely something wrong with Superman's flight. How is he able to do this? Force is equal to mass times acceleration. However, when Superman flies, it's got to be a force going up minus gravity, and it's going to be equal to 0 because there's no acceleration in the y direction. But where does this force come from? Birds are able to fly because they create a force going downwards with their wings. Superman doesn't have wings, so how is he able to fly? I guess the only explanation is that he is a superhero, and that he came from a different planet called Krypton. Next, we're going to look at Peter Parker, also known as Spider-Man, for an example about trajectory. We're going to be using the kinematic formula r is equal to v initial squared times sine of 2 theta over g. We're going to say that the buildings are approximately 6 meters apart, which is about 20 feet, and have a common height. Peter Parker is going to be jumping at an approximately 45-degree angle, and his initial velocity is going to be 5 meters per second. Now we're going to plug in numbers. And when you plug it into your calculator, you're going to get approximately r is equal to 2.6 meters, which is approximately 8 feet. That's not nearly long enough of a jump to make it to the other buildings. And so, could Peter Parker make it to the other building? Perhaps. It just depends on how far the buildings are apart. There's also another controversy with Spider-Man. In The Amazing Adventures of Spider-Man, number 121, Spider-Man's girlfriend, Gwen Stacy, is thrown off the roof of a tall building while he is fighting the Green Goblin. Spider-Man uses his web to catch her, but her neck snaps and she dies. The Green Goblin taunts Spider-Man that it was the fall that killed her. However, that would draw some pretty bad conclusions for skydivers. So we're going to use some physics to prove that it was the webs that killed her, not the fall. We're going to assume that the height of the building is about 300 feet, which is 91.4 meters. Using that, distance is equal to average speed times time. Average speed is equal to velocity initial plus velocity final over 2. Therefore, velocity over 2 is equal to average speed. Acceleration is equal to g, which is also equal to the change in speed over time. Therefore, distance is equal to velocity squared over 2g. Plugging those numbers into your calculator, we find that velocity is equal to 95 miles per hour. But what kind of force does that apply on her? We're going to say that the change in time is half a second and that her mass is 50 kilograms. We're going to apply Newton's second law, force equals mass times acceleration. Acceleration is also equal to the change in velocity over the time. Plugging in the numbers, we get that the force is 1,100 pounds. That's 10 Gs, so it's no wonder that her neck snapped. The typical astronaut is only trained for 3 Gs. So we've proved it. It was the webs that killed her, not the fall. Now we're going to look at a scene from the X-Men where someone walks through a wall.
Bye, Professor.
Bye, Kitty.
String theorists actually believe that this could happen. It all began with a cat and quantum physics. The cat was named Schrodinger's cat because Schrodinger, its owner, put it in a box with an atom. This atom had a 50-50 chance of decaying. If it decayed, it would emit a gas and the cat would die. If it didn't decay, the cat lived. Schrodinger declared that because there were 2 possible scenarios, there were 2 parallel universes, and thus the cat was half alive and half dead. Confusing, right? Well, string theorists believe in this, that every possibility has its own parallel universe. So Katie being able to walk through walls is potentially possible, but for normal people, the chances are very slim. Next, we're going to look at another X-Men clip involving the character Cyclops. The explanation for how this defies physics is quite simple. It's Newton's third law, which states that for every action there is an equal and opposite reaction. When Cyclops' eyes shoot the beams, his neck should snap back in an equal and opposite reaction. This does not happen, however.